Switzerland. So in this work we're taking the 3D models of buildings and trying to decompose them into architecturally meaningful parts. That is actually parts that make semantic sense, like walls, towers, colonnades, whatever. We're doing it in a completely unsupervised way, so there's no training needed ahead. And as we show in our results, and you can maybe see in these pictures, although they're not of the best quality, we deal with quite complex shapes. So the standard approach to this problem is basically primitive fitting. So if I want to detect this tower, I would say, okay, the tower is somehow cylindrical, so I would try to fit the cylinder. The problem is the tower is exactly not cylindrical, but is rather a set of different cylinders, all stacked on each other. So I have to detect all these cylinders and then try to merge them. Instead of doing that, we say, okay, it's not really a set of cylindrical but cylinders, but the property it has is that it's rotational symmetric. So the easier ways would be just to detect a rotation symmetry, and when you have it, you basically have your tower detected. And that's exactly what we do in our paper. So we detect a couple of different ways of types of symmetries, namely the mirror symmetry and the rotational symmetries, that are supposed to explain the majority of parts of the buildings. For the parts of the buildings that are not explained by the symmetries, we extract the floor plans, like these gates in front of the castle. And when we have these cues extracted, we try to run global optimization to find these parts. I will definitely not go into the details of the optimization now, but in essence, for every point we try to assign a we try to assign a label to which architectural component does it belong. So that's what the first part of optimization is responsible for. The second part of optimization tries to make it in a smooth way. So picks points that are close by should be likely to have the same label. And the third part is in charge of preventing too many objects to be detected, because obviously symmetry detection can generate some false positives. Yes, false positives. And you have to do something with that. That's it. We show results on multiple data sets and compare it with multiple baselines. I can show you more data sets at the poster section after the dinner. We also show the baselines that we don't show in the paper, so it's really important to visit the poster session and me there. We also show that it works on pretty rough data sets. For example, this is the aerial data, where you literally have a couple of dozens of points per building, and we're still successfully able to decompose it into parts. So that's actually it. Just to sum it up, we have buildings and we can decompose it into parts. So for example, here we have a castle that you can decompose into towers, gates, walls, and so on. If it's a simpler building, you just decompose it into like 4 walls. And this is actually pretty cool because you have a lot of applications for that. Generally, to begin with, if you have models for every part of your building, you can just replace it with a better model. So if I have a nice 3D representation of a tower, I can just put it instead of my lousy set of 3D points I have. Also, I understand how the building looks like. So for example, I know that this part of the building is the part that has a lot of towers, so it can be useful in many things like indoor navigation, for example. And also we basically know of which parts does a building of which parts make the building. So you can say this is a building that is fancy because it has a lot of towers, or this is a building that is not fancy, like the building number 2, because it only has 4 walls. And that's why that would be very helpful for detecting landmarks. That is actually quite an actual problem if you have a large city-scale datasets and you want to facilitate different qualities of reconstructions on different buildings. That's it. Looking forward to seeing you to the poster.